Welcome to this definitive guide on Retrieval-Augmented Generation or RAG. This material serves as the practical blueprint for building powerful, production-ready AI applications that are capable of leveraging your organization's own data. RAG is fundamentally important today based on the assertion that 90% of use cases currently being worked on in all companies are specifically related to RAG. To understand why RAG is necessary, we must first look at the dilemma of a standalone LLM. While large language models are incredibly powerful, they face critical limitations for real-world business applications. These limitations fall into three main categories. Knowledge cutoff. LLMs are trained on data up to a specific point in time and therefore have no knowledge of recent events. To understand this statement, like for instance, an LLM trained until August 1st won't know what happened between August 1st and August 31st. So the data that is present between this 30 days won't be available at the LLM. Okay, that's what it means. And if you ask any questions, okay, like after that's from the time period of 1st August till 31st August, it won't be able to answer, but it will try to answer in such a way that it will make you believe that the answer, whatever that LLM is providing, is true. Okay, so it won't give you like a sentence that I don't know this particular answer, but it will try to give you some other answer based on how the model was trained on 1st of August. Okay. So it also has a privacy barrier. LLMs are not trained on private or internal knowledge bases, meaning they do not know your company's specific HR policies, financial data, or startup documentation. This means that even LLMs are like generally trained. Okay, suppose if you are working in company ABC, for example, and you or the company will have some of its rules or regulations, those won't be known by the LLM, or the HR policies won't be known for the LLM. Okay, to give you an example, a simplest one, if you ask like how much the leaves we have for the annual period, it will just give you an answer which is known to him based on whatever the models that was initially trained on. Okay, so it won't give you an exact answer that how much your company leaves like allocates the leaves to you yearly, but it will give you a general answer. So that what the statements mean. um, Hallucination. When an LLM lacks necessary information to answer question, it frequently generates plausible but incorrect or fabricated answer. As the source puts it, the model does not want to look like a fool. So this is what it's been explained earlier in 2 points, that it is going to give you some incorrect or any answer, fabricated answer, to make you believe that whatever it is answering is true, and it doesn't want to be like, not to give you it generally won't give you the question like answer like I don't know this particular statement, or I don't know this what's the policy, but it is going to give you a certain answer. So that is what hallucination means. One alternative to address this limitation is fine tuning, but this is often not the right tool for the job. Fine tuning is an expensive alternative process characterized by high cost and complexity. Fine tuning an LLM with billions of parameters is very expensive and tedious process, demanding significant computational resources and expertise. Furthermore, it suffers from a lack of agility. Internal data such as company policies is constantly updated, and you cannot afford to fine-tune the model daily or weekly, making it unsustainable for dynamic knowledge bases. This is where RAG provides a solution. RAG is defined as the process of optimizing the output of a large language model, so it references an authoritative knowledge base outside of its training data source before generating a response. The core philosophy is simple. Instead of retraining the model, we augment it. We provide the LLM with relevant, just-in-time information from an external source, allowing it to generate accurate, context-aware answers without changing its core parameters. The key benefits of RAG are that it is cost-effective and agile. It significantly reduces hallucination by providing factual context, and it allows LLMs to access both private and real-time data. The RAG system is built upon two major phases: the offline process, building the knowledge base, and the online process, generating the answers. Okay. The offline process is the data ingestion pipeline. So we'll just have a brief look at about this in a very theoretical way to understand what exactly does it mean. Okay. So now here, one second. Okay. So here we have two processes, like one is offline process, that is we are building the knowledge base, and another is online process of generating the answer. First we'll understand about offline. The offline process is the data ingestion pipeline designed to transform raw unstructured documents into a structured queryable knowledge base. Okay. So here are the components: the data source and the loads, the data sources and the loads. We start with various data format. It can be PDFs, HTMLs, Excel, SQL databases, and more, and use document loaders to read the data from its sources. Before any further processing, the loaded data is converted into a standardized document format. The standardized structures includes the page content, which is the actual tags, the what, and the metadata, which contains additional information like the source, page number, author, file type, the where, who, and the when. Effective uses of this metadata is critical for powerful queries later on, such as filtering results by specific authors. Just to break down this, so first what we have mentioned is the page content, okay, which is the actual text will be there. So what does it mean? That it will, let's take an example of a leave policy only, okay. So it will have like how many how many leaves are like allocated on a yearly basis, okay, and how many sick leaves will be there, how many your PLs will be there. So those, for example, those 2 points will be there, and in the same way, so that is what the page content is. Okay, actually the what, and the metadata is like that policy that we are uploading. Say if it's a PDF file, so from which source we have gotten, how many pages are there, who's the author. It will have an author name or maybe say the company's name on it. So there's sort of like the file tab. Suppose we are either giving it into a PDF format or Excel format. So this information is called as a metadata, and what are the contents of that actual page or the actual written words on this page is called as a page contents. Okay. So then here after that the next process will be chunking. Okay. So parsing and chunking. We split this. We must split the content into smaller, manageable, and often overlapping chunks, because LLMs and embedding models have fixed context size. For example, you cannot feed a 100-page PDF directly into a model, right? By splitting the document example into 1,000-character chunks with overlap, we ensure the content fits within the model's context video and help retain context between those chunks. Embedded and store. The final step involves embedding. The embedding models convert each text into chunks, into a numerical vector, a list of numbers. These numerical representation of your data are saved as vectors, embeddings, along with the associated text and metadata in a vector database. The power of this approach is that semantically similar text chunks have vectors that are numerically close to each other, allowing sorry allowing us to find relevant information by searching for vector proximity rather than just performing the keyword matching. Now we'll see about this online process. We have just understood this, right? The online process is the retrieval and generation pipeline, which is executed in real time to find the most relevant information for a user's query and use it to generate a precise context aware answer. So what happens here is user query. When a user asks a question, example, what are leaf policies? The system uses the same embedding model employed during ingestion to convert the user's query into a vector. Okay. Search vector TP and retrieve relevant content. The system performs a similarity search on the vector database to find the stored document chunks whose vectors are closest to the query vector. The top key most similar chunks are retrieved. This is called the contest. Augmented prompt and send it to the LLM. This leads to the core mechanism prompt augmentation. The retrieve contest is combined with the original user query to create a new comprehensive prompt for LLM. This augmented prompt explicitly instructs LLM to use the provided context to answer the question concisely. For example, the prompt includes the retrieve chunks as context and the user query as question. Generate the LLM receives this augmented prompt and generates a final human-like text based only on the retrieve context. This ensures the answer is precise and authoritative, drawn directly from your knowledge base. Okay. So let's go a deep dive. Let's have this here. So we just understand it. Okay, the data ingestion pipeline that it transforms raw unstructured document into structured queryable knowledge base. This process consists of 5 main steps: the data sources, the load, parse and chunk, embed and store. Let's have a basic look at it. So data stored, we start with the data in any format such as PDF, HTML, Excel, and SQL anything it can be. So we then load these documents into the document loaders to read the data from its sources. Then the documents are read the content and split it into smaller manageable chunks. Okay. Then embedding happens where we convert each text chunk into a numerical vector using an embedding model. Then these vectors they save into an embedding, like save the vectors, embeddings, and the associated text meta into a vector database. Okay. Uh, Before processing like chunking or embedding occurs, all loaded data is converted into a standardized document format. Okay. Uh, Document format which is essential for processing and retrieval. This standardized structure includes two parts. The first is the page content. Okay, we have just explained and understood in the earlier slide. This is an actual text content from the source file referred to as what, and then the second C is metadata. Okay, this includes additional information about the content, the where, who, when, such as the source file, page number, author, or file type. Okay, the effective use of this metadata is critical for executing powerful queries, such as searching for information only within documents by a specific author or from a certain source file. This slide focuses on mechanics of text preparation, chunking, why we split the text. The problem is that LLMs and embedding models have fixed context size, meaning you cannot feed a 100-page PDF directly into them. The solution is to split the document into smaller overlapping chunks, example 1,000 characters each, and then feed that within the model's context video, with the overlapping helping retain context between the chunks. Embedding, how we search text. An embedding model converts text chunks into numerical vectors. The power of this approach is that in the resulting vector space, semantically similar texts have vectors that are numerically close to each other. This proximity allows the system to find relevant information by searching for vector proximity instead of relying solely on keyword matching. Here we are just going for the retrieval and the generation pipeline. It has these main 6 components, that is a user query, the embed query, the search vector DP, retrieve relevant context, augment prompts, send to LLMs and generate. Uh, this pipeline is designed to find the most relevant information for user's query and use it to generate a precise context-aware answer. Okay, the steps are sequential as we have seen it. Like first is a user query. The process begins when the user asks a question: "What are our leave policies?" For example, is the same way how we ask maybe a chat GPT. You can just take an example. Okay, the embed query. The system uses the same embedding models used during ingestion to convert the user's query into a vector. Search vector DB. The system performs a similarity search in the vector database to find the stored document chunks whose vectors are closest to the query vector. Retrieve relevant context. The top key most similar chunks are retrieved, which which consist of the context. Augment prompt and send it to the LLM generation. The retrieve context is combined with the original user query into a new comprehensive prompt for the LLM. The augmented prompt is sent to the LLM, which then generates a final answer based only on the provided context. The core of RAG relies on prompt augmentation, which is described as a clever form of prompt engineering. A new prompt is created that explicitly instructs the LLM to use the information that has been retrieved. For example, the prompt structure provides the command: use the following context to answer the question concisely, followed by the retrieve chunks, context, and the user query questions. Okay. By doing this, the LLM receives the precise authoritative information it needs to answer the question accurately, drawing directly from the established knowledge base. From blueprint to reality, building a RAG pipeline is accessible due to powerful open source libraries. The core component used in an implementation include like a LangChain, the primary framework for orchestrating the entire pipeline, offering abstractions for loaders, splitters, and chains. Sentence transformers, a library utilized for easily using state-of-art embedding models. ChromaDB and Fez, open source vector stores used to save and efficiently search through document embeddings, where Chroma is used for ease of setup and Fez is used for performance. PyMu-PDF and PyPDF specialized load are necessary for efficiently parsing PDF documents, which are common data source for knowledge bases. Grok or OpenAI. These represent underlying LLMs that perform the final generation step. Practical implementation demonstrate how knowledge is ingested. Loading the documents we will be using, the directory loader is used to efficiently process all files in a folder, specifying the PyMu PDF loader to handle the PDF parsing. Chunking documents, the recursive character text splitter is used to intelligently split documents into chunks of a specified size. Enhancing the output. A crucial aspect of production-ready RAG application is enhancing the output for trust and variability. The problem is that while a generated answer is useful, a trustworthy answer is essential when a user needs to know where the information came from. The solution is to enhance the RAG function to return not just the output but also source documents and associated metadata. This builds user trust and allows for easy fact-checking, thereby transforming the application from a black box into a transparent knowledge tool. To transition from a prototype script to a production system, the code should be organized into a modular code structure. This separate concerns making the application easy to maintain and extend. Key module with the source directory include dataloader.py, a module dedicated to loading and processing the documents, embedding.py, a class designed to handle chunking and embedding, vector store manages all interaction with the vector database, search integrates various components to generate a final response. App.py serves as the main entry point for the application. The structure represents the necessary leap from a simple script to robust software solutions. Okay, so this is like a brief video on the rack. We will try to make a detailed video or maybe a detailed implementation of it. So thanks for watching this video.